The mean value theorem. Assume that f is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Let's pause and try to make sense of the hypothesis. To use the mean value theorem, I need a function f that's continuous on a closed interval from a to b. So on this picture, I have this function f of x, this black curve, that's defined on the interval from a to b. Now, I want it to be continuous on the closed interval, closed meaning I include the endpoints. So this function, I can draw it without lifting my pencil. I am continuous on this closed interval from a to b. But I also need it to be differentiable on the open interval from a to b. So differentiable means that I can find its derivative at any point between a and b. I can find the slope of the tangent line. So in other words, what I cannot have is no vertical tangent lines and no cusps or corners anywhere between a and b. Now, because it's an open interval, I can have a cusp or a corner at the endpoint. So I could have this little cusp happening at the endpoint. I just need no cusps, corners, or vertical tangents in between a and b. Now, if that is satisfied, then the conclusion of the mean value theorem says that there has to exist at least one value c in the open interval from a to b, such that f prime of c equals f of b minus f of a over b minus a. So let's try to make sense of the conclusion. First of all, the conclusion is only an existence theorem. So this theorem is considered to be an existence theorem only because I'm not actually going to be able to find this c value in most cases, just show that one exists. So there's this c value, and it's ultimately an x value. It's going to come from the x-axis, so I want this c to be between a and b on the x-axis, such that f prime of c equals f of b minus f of a over b minus a. So let's remind ourselves that f of b and f of a are y values. So this is like a y2 minus y1 over x2 minus x1. So in other words, this is a slope. And in particular, it's the slope between these two endpoints here. So this is the coordinate point AF of A, and this over here is the coordinate point of BF of B. So this right-hand part of this equation is the slope between these 2 points, or the slope of a secant line. So this portion is the slope of the secant line that passes through AF of A and BF of B. Alright, so what this says is there's going to be at least one c value between a and b, such that f prime of c, so f prime of c is a derivative. A derivative is the slope of a tangent line. So this is the slope of the tangent line through cf of c. So what this is saying is there's at least one value where the slope of the tangent line is equal to the slope of the secant line at the endpoints. So AF of A and BF of B are the endpoints. So I'm going to be able to find one x value between A and B at least, such that the slope of the tangent line is the same as the slope of the secant line. So this green line and this red line here are parallel. They have the same slope. So by the mean value theorem, you're always guaranteed to find at least one such value where the slope of the tangent line is equal to the slope of the secant line. Alright, in this first example, we want to find a point C satisfying the conclusion of the mean value theorem given the function the square root of x on the closed interval from 4 to 9. Now before we can satisfy the conclusion of the mean value theorem, we have to make sure that the function satisfies the hypothesis. So we need to make sure that on the interval from 4 to 9, the closed interval from 4 to 9, our function is continuous and differentiable. So we should know that the function square root of x looks like this. Its domain is from 0 to infinity, and it's continuous and differentiable from 0 to infinity. So we just want to note that f of x is continuous and differentiable on 0 to infinity. Or we can put more specifically on 4 to 9 so that we can even use the mean value theorem. So we satisfied the hypothesis. Now our goal is to attempt to actually find that point C. So the mean value theorem guarantees this point C's existence because I satisfy the hypothesis, continuous and differentiable. But even more than that, I want to find this point. So let's rewrite the conclusion that f prime of C is going to have to equal f of B. Well, my B value is 9, so f of 9 minus f of A being 4 in this case, over 9 minus 4, or B minus A. So I'm going to need to find a point C such that f prime of C equals f of 9 minus f of 4 over 9 minus 4. Well, f of 9, substituting 9 into the square root function, I get the square root of 9 minus the square root of 4 over 5. 9 minus 4 is 5. The square root of 9 is 3. The square root of 4 is 2. So, and this is over 5. So f prime of C is going to have to equal 1 over 5. So I'm going to need to find a C value such that f prime of C equals 1 over 5. Well, first I'm going to need f prime of x. So f prime of x, the derivative of the square root of x, remember this is x to the 1 over 2, so this is 1 over 2 x to the negative 1 over 2, or 1 over 2 rad x. So what I'm really doing is I'm solving, when does 1 over 2 square root of x equal 1 over 5? Whatever that value is, that's going to be my C. So let me change colors. We're setting up the equation, when does 1 over 2 radical x equal 1 over 5? So now, let's attempt to go ahead and solve this. I'm going to do this by cross multiplying, so I'm going to get 5 equals 2 rad x. So if I want to solve for x, I'm going to square both sides. So let's go ahead and square both sides. I get 25 equals 4x, because if I square root of x, I'm going to get just x out, and I do have to square the 2 also. I can distribute this exponent because this is multiplication. And then I'm going to divide both sides by 4. So x equals 25 over 4. So this x value is in fact my C value. So at x equals 25 over 4, this is where the slope of the tangent line equals the slope of the secant line. So let's actually try to make sure that this worked out. So this is my value. This is my answer, 25 over 4. So let's go ahead and draw the secant line. So the line going through the endpoints, actually, whoops, doesn't go through 0, goes through 4 and 9. So the secant line is the line that connects those 2 points. And I want to make sure that the tangent line that goes through 25 over 4, so 25 over 4 is like 6 1/4, so maybe about right here. So let me go up and try to draw a tangent line right there. If I were to do that, I try to make it so they look parallel, they would have to be parallel lines. So the slope of the tangent line at 6 1/4 has to be the same as the slope of the secant line that goes through 4f of 4 and 9f of 9. So in this case, we actually could find that C value that was guaranteed by the mean value theorem. Alright, in the next example, find the point C in the interval from 1 to 3 open, where the slope of the tangent line is equal to the slope of the secant line on the graph of f of x equals x cubed. Alright, so same type of problem, it's just understanding the wording. So this is basically saying that satisfies the conclusion of the mean value theorem, which is the slope of the tangent line has to equal the slope of the secant line over the endpoints, 1f of 1 and 3f of 3. So we can go ahead and sketch the graph of this just as our own personal justification towards the end. So the graph of x cubed is going to look something like this. And we're concerned with what's happening between 1 and 3. So we know x cubed is a polynomial. It's continuous and differentiable everywhere. So we can start out by saying, note f of x is a polynomial. We'll abbreviate that. So it's continuous and differentiable everywhere. So we know that one such value even exists. Alright, so now we're going to need to find f prime of C such that f of 3 minus f of 1 over 3 minus 1 equals that f prime of C. So f of 3, 3 cubed is 27. 1 cubed is 1 over 2. So we get 26 divided by 2, or 13. So ultimately, we need to set the derivative equal to 13 and solve for that value. So this is a nice one. The derivative of f of x is 3x squared. So we're setting 3x squared equal to 13 and solving for x. So I get x squared equals 13 over 3. So x is plus or minus the square root of 13 over 3. So I got out two different values, but drawing the graph sometimes helps make sense of that. So the slope of the secant line that passes through 1, 3 looks something like this. There's that, kind of messed up a little, but there's that secant line right there. And I'm trying to find that point where the slope of the tangent line is going to end up being the same. And I got two different values out. Well, these two different values represent the two places on the graph where the slope of the tangent line is 13. So notice it's also going to happen over here. But I wanted the point C in this interval. So we're basically going to ignore the negative. So the only answer is positive radical 13 over 3. And that's the number that satisfies the conclusion of the MVT, which is, in words, what this problem is asking me to do. Alright, in this next example, we have the following table represents the position of a particle in inches where time is in seconds. Note that f is differentiable everywhere. So here I have time in seconds, so I know exactly where the particle is, its position at 0, 1, 3, 4, and 6 seconds. And its position is 2, 5, 6, 9, and 11 inches. Now in part A, is the particle ever at exactly 7 inches? Explain. So this first part is actually a review problem. So here's this position function, and I know at time 3 seconds the particle is at 6 inches, and at 4 seconds the particle is at 9 inches. So what we're using here is the Intermediate Value Theorem. So sometime between 3 and 4 seconds, the particle has to have been 7 inches because my function is continuous. So the Intermediate Value Theorem is the theorem I'm using, which requires a continuous function. Now, how do I know that the function is continuous? Because differentiable implies continuous. So we're going to start out by saying, since f of x is differentiable, it's continuous. By the Intermediate Value Theorem, since 7 falls between, I don't want to say since 7 falls between 6 and 9. I want to say since 7 is between s of 3 and s of 4. So of course 7 is between 6 and 9, but I want to reference the function. So since 7 is between s of 3, which is 6, so this quantity is 6, so you wouldn't actually write the 6 above it, but just for our own knowledge and information to understand this problem, since 7 is greater than s of 3, or s of 3 is less than 7, and 7 is less than s of 4, so s of 4 being 9, there must be some t in the interval from 3 to 4. So remember, there must be some time. Time was happening between 3 and 4 when the position was 6 and 9. So there must be some time in 3 to 4 such that s of t equals 7. So this first part is review, but typically when given a table of data, we're asked for an intermediate value theorem question as well as a mean value theorem question quite often. So in part B, is the particle ever traveling at a velocity of exactly 3 feet per second? Explain. Alright, so we're given this table that has to do with position, but we're asked a question about velocity. So is the particle ever traveling at a velocity? Is v of t ever exactly 3? This is the question that we're being asked. Is this true? Is there a time when this happens? Well, we have to relate that back to position. So it's like being asked, is there any time when s prime of t equals 3? So this is where the mean value theorem is going to come into play, because this is asking for whether or not something happens, not asking for a particular time. So is the particle ever traveling at a velocity of exactly 3 feet per second? We don't actually have to find it. So we go to our existence theorems. We already used the intermediate value theorem. Now we're going to use the mean value theorem. So does there exist a time when s prime of t equals 3? Well, if I can find where 2 points where the slope of the secant line between those 2 points equals 3, then there's some place where the slope of the tangent line equals 3. So it's like we're trying to find, is there some t1 and t0 such that s prime of t1, or not prime, s of t1 minus s of t0 over t1 minus t0 equals 3. So looking at this table is a bunch of points. The points are 0, 2, 1, 5, 3, 6, 4, 9, and 6, 11. So these are a bunch of coordinate points. So can I choose any pair of coordinate points and have the slope be 3? Because if I can, then over that time interval, there must be a place where the derivative, which is velocity, has to equal 3. So let's check between these first 2 points. If I do y2 minus y1, I'm going to get 5 minus 2, which is 3, over 1 minus 0, which is 1. So I found it. In this first time interval, I found it. Now if I didn't, I would just have to keep going between these 2 points. But they don't have to be consecutive points. I could also have chosen this coordinate point and this coordinate point and subtracted. So I could have gotten 6 minus 2 over 3 minus 0. As a possibility, which of course doesn't work, but you can try all the different combinations of these coordinate points. It just so happened that the first 2 points did work out. So between 0, 2 and 1, 5. So the answer is then yes. So it's just a matter of explaining why. So what we're going to say is, since f is differentiable and continuous everywhere, by the mean value theorem, so by the MVT, there is a time t in the interval from 0 to 1, so the time interval is 0 to 1, such that v of t, or s prime of t, equals 3, since s of 1 minus s of 0 over 1 minus 0, well, that equals 5 minus 2 over 1 minus 0 equals 3 feet per second, really, because the units of position are in feet and the unit of time is in seconds, so this is feet over second, so 3 feet per second.